All right, now we're going to look at how to do substitution with definite integrals. So if you do it with definite integrals, you're going to have those limits there. So the key with doing those is we're going to do our substitution, but we also need to then change what those limits are to a function of u. Let's look at an example. So we want to integrate this using substitution. Here you can see we have the graph of square root of 2x plus 1. The graph would look like that. We're integrating from 0 to 4, so the area that we're trying to find is this area right in here. We could estimate what that is. It looks like it's going to be 1, 2, 3, 4, 5, 6. This is about 7 together, maybe. These are close to 8, so it's going to be a little bit more than 8 when we do that. So now we got to figure out what's the exact one though, and we can do that by integrating. However, this one is a little bit harder to integrate, so let's use some substitution. Our function in a function there would be 2x plus 1, and so derivative would be 2 dx there. So I'm going to move that 2 to the other side by dividing, so we're going to have 1/2 du here. So substituting in now, we're going to have this half, that extra half when we substitute in here to change it to du. We're going to have square root of u here, because that's what our substitution was for u. But now we got those limits. So what we're going to do is also change the limits. And by doing this, we won't have to substitute back in later. So if we change our limits of integration here, we're going to do that with our u substitution here that we use. So what we're going to figure out is if we substituted 0 in place of x, what would u turn into? So we'd end up with 2 times 0 plus 1, which would equal 1. So now our new limit over here, 0, changes to 1. Let's do the same thing with 4. So if we change 4, 2 times 4 is 8, plus 1 is 9. So this limit here changes to 9. To solve this one now, we got 9 to 1. Let's change this to a half again for our integration. So antiderivative would be u to the 3/2. Reciprocal is 2/3. We got to keep that 1/2 with us, and we want to evaluate it here from 9 to 1. Now, what we said before is since we've changed these limits now, there's no need to substitute back in for u. We can just solve this with u there, and that's usually easier than having to substitute back in. I'm going to simplify there. So now we got 1/3. If we plug 9 in, this is going to be 9 to the 3/2 power minus 1 to the 3/2 power. And to simplify that, you could use a calculator. If you didn't have a calculator on this, they could expect you to still do that. Remember this notation here of 3/2. The bottom number is your root, so this would be like the square root of 9, and then the top number would be an exponent to the 3rd power. Same over here, it'd be like square root of 1 to 1/3, but 1's easy because 1 to any power is still 1. And so now you got, this would end up being 3 to the 3rd power, which is 27 minus 1, or we get an answer of 26/3. So that would be the exact answer, which is the same as 8 2/3, and we had said that area should come out to be a little bit more than 8. What we did on this one is we changed our integral when we substituted from this with this graph to this, which if you graph out square root of u over 2, because we got that 1/2 there, you get this graph now from 1 to 9, because remember we changed our limits here, so 1 to 9. And that area ends up being the equivalent area to the graph above it. If you look here, 1, 2, 3, 4, 5, and then we got like about 6, 7, 8, and a little bit more than 8 squares here, same area, about 8 2/3, and it comes out to be exactly the same. So we're changing it to something equivalent when you change it with a substitution. All right, let's have you guys try this one, see what you come up with. All right, our function in the function here would be x squared. Finding derivative here, we get 2x dx. I see that x out in front, so we'll leave that x there, and then we got half du. So this turns into our u, the x and the dx together change into our du. So now we're left with the integral of cosine u. We got that extra 1/2 I'm going to write out here. And now we want to change our limits. So if you put 0 in, now we got 0 squared, which is still 0. So this one stays at 0. If we put the other one in, pi, now it's pi squared. There's not really a way to simplify pi squared, so let's just leave it as pi squared here. Okay, so now we want to find that antiderivative. Antiderivative cosine is sine. We got that 1/2 we need to bring with, plus c, or sorry, not plus c on this one. This is a definite one, so we need to evaluate it at pi squared and 0. So what we end up with is 1/2 sine of pi squared minus sine of 0. If you think about sine 0 for a unit circle here, angle of 0 is right on our line here, right here. That order pair is 1, 0. Remember, our x value is cosine, our y value is sine, and so sine of 0 is 0 here. So we end up with 1/2 sine of pi squared minus 0. Sine of pi squared we can't really simplify to a nice number, so probably on a test you're just going to see the answer written as 1/2 sine of pi squared, and that would be the exact answer. If it was a calculator one, then of course you could round it off if the approximation is needed.